So here, the chapter on wave optics, where we talk about why the soap bubbles are brilliantly colored in sunlight. Why, if you look at a compact disc reflecting light, it looks colored again. So here we go. So here is the first question that says, show that when light passes from air to water, its wavelength decreases to 0.750 times its original value. Well, does the wavelength of light change when it goes from one material to another? Yes, of course. Does the frequency of light change? Never. Frequency determines the color. So, when blue light passes from air into water, it's never going to become green. It's always going to stay blue. So frequency never changes, but wavelength and speed both change. And to find the change in the wavelength, all you got to do is divide the wavelength in air by the refractive index of the material. So in air, the wavelength is assumed to be lambda, and the refractive index of water is 1.333, which gives 0.750 times the wavelength in air. And so that's how the soap bubbles look in sunlight. And here is a laser beam passing through a grid of vertical slits. So you have tiny, very thin slits, and if you pass a laser beam through that, it's going to produce this pattern. And same thing happens when you look at an oil slick and light shines into it, like a thin film of oil maybe on the surface of water, and light shines into it. Again, it looks brilliantly colored. Now, all this can be explained using wave optics, or considering the fact that light travels in the form of waves. Okay, so that's what we're trying to do. But to start off, we need to compare light with sound. Now, sound can bend around doors and go into the room, so somebody on the other side can hear you. That's because the wavelength of sound is really big. So when the wavelength is big, it's able to bend more. But since the wavelength of light is really tiny, it bends just a tiny bit. And this bending of light around the edges of obstacles is called diffraction. So light bends around the edges of obstacles, and if the obstacle is tiny, like a slit, now the wavelength is approximately of the order of that slit, and that's when the bending effects become prominent or pronounced. So light bends around the edges of tiny obstacles, and this is called diffraction. And here you can see how light bends. So when the opening is big, the bending is less. As the opening becomes smaller, the bending effects become larger. And here in this case, when the slit or opening is really narrow, that's when light diffracts the most. Now, Thomas Young performed an experiment in which he had two slits, parallel slits, very close to each other, on a cardboard as shown here, through which sunlight was allowed to pass, and on the other side there was a screen kept. On the screen he observed alternate dark and bright bands. Now what is expected is just two bright patches of light, but what he obtained was a large number of bands that are alternating bright and dark. Now this is called the double slit experiment, and this phenomenon can be explained using interference, as we're going to see. But there are some conditions for interference to be produced. Number one, the sources must be coherent. A coherent source produces waves that are in phase with each other, or there is a constant phase difference between them. So the phase difference does not keep changing. It's just a constant. Either there is no phase difference or there is a constant phase difference. That's what you mean by coherent sources. And in interference, you have constructive interference and destructive interference. So as you can see in the diagram, you see these waves here. That's the wave, the crest and the trough, the crest and the trough. And again, if you look at all these waves, they're exactly lined up. Their crests are lined up, their troughs are also lined up. So when these type of waves interfere, you're going to get constructive interference. They're going to support each other. So the amplitude is going to increase. On the other hand, if you look at these two waves here, you can see that the crest is lined up with the trough of the second one. Here the trough is lined up with the crest. So they are 180 degrees out of phase. One is positive, the other is negative. Therefore, when such waves are superimposed, they cancel out. See what you get? You just get a line. So there is no vibration at all. This is called destructive interference. But look at this. Here, the amplitude of each wave is equal, but after they are superimposed, it's actually double. So this is the difference between constructive and destructive interference. So in constructive interference, you have a crest and a crest, or a trough and a trough coming together. In destructive interference, on the other hand, you have a crest coming together with a trough. That's why they cancel out. Action. So this diagram illustrates what I have just explained. You have the sunlight coming in, falling on the two slits, S1 and S2, and from those tiny narrow slits there is diffraction, so the waves bend and go in all kinds of directions. The same thing happens here, and the waves from S1 fall on the waves from S2, so they interfere. And if you look at the darker lines, that's where you have a crest and a crest. Now that's actually a crest. The dotted lines are troughs. Okay? So if you look carefully, and I hope you can see it, you see the crest from one wave meeting a crest from the other one. The other ones are shown lighter. So this is a point where the crest and the crest meet. So if you follow this line, all along this line, you're going to see a crest falling on a crest. That produces a maxima. A crest falling on a crest produces a maxima. So on the screen here, you will get maximum. But here you have points where you have crest and a trough. Trough and a crest, crest and a trough. So you get a minima. At the center of the screen, which is here, you're going to have a maximum. So at the center, you have a maximum. And on the sides, above and below the maximum, you're going to have dark and bright and dark and bright. So central one is maximum, then you have a minimum, and then you have a maximum, and so on both sides. So light spreads out from each slit because the slits are narrow, that is diffraction. These waves overlap and interfere constructively and destructively. and we can see the dark and bright bands produced on the screen. Here it's the same diagram on top, but here these are water waves. The water waves kind of replicate what happens with light, but it's here it's much more clearer. You see the crests from each one. So you see the point where the crests are coming together, you get brightness. But where you have the crest and the trough, you're going to get darkness. In fact, this is the type of image that you get on a screen. See the central, you see the central bright one, and then you have, if you look carefully, you see a dark patch, and then next bright, again dark, next bright. So this is one side of the screen. Only one half of the screen is shown here. So here we have some geometrical ideas that are coming in. If you look at a point on the screen, like this point, you have waves from slit 1 and from slit 2 reaching that point. But we can see that the waves from slit 2 travel a greater distance. So they have a greater path. So this diagram shows you that we can find the path difference geometrically. But before we get there, if the crest from one reaches the trough of another, you're going to get destructive interference. On the other hand, here you have both the crests coming together, you get constructive interference. So depending on what point you're looking at on the screen, you're going to either have constructive or destructive interference. Because as the path difference changes, you will have constructive or destructive. Geometrically, to find the path difference, you see, let little d be the distance between the slits, little d, and then you drop a perpendicular from this slit to the other ray. This is actually going to be the path difference. And from this triangle, we can show that this path difference is d sine of this angle, theta. So remember that the path difference is going to be d sine theta. We're going to use that a lot. D is the distance between the slits, and theta is the angle. So if you take a point further above, you see that when you draw those two lines, the angle is going to become bigger. While at the center of the screen, that angle is going to become 0. So the path difference is d sine theta. Okay? And whenever the path difference becomes equal to m times lambda, because if the path difference is one wavelength, then you would have the 6th crest from here falling on the 7th crest. So you would get constructive interference. You could have the 6th and the 8th coming together. Again, you have constructive interference. So the condition for constructive interference is that d sine theta is equal to m lambda, where m is an integer. It can take values 0, 1, 2, 3, 4, etc., both positive and negative. So it can either be 0, 1, -1, 2, -2. Why negatives and positive? Because on one side of the screen you have positive, on the other side of the screen you have negative, and the center corresponds to when m is equal to 0. So the condition for constructive interference is d sine theta is equal to m lambda. Now when do you get destructive interference? That's when you have a crest falling on a trough, right? What's the distance between a crest and a trough? It's half a wavelength. So if the crest from here falls on the next trough from here, the path difference is half the wavelength. You would get destructive interference. Or if you have 1.5 times the wavelength, again you get the same. So the condition for destructive interference is that d sine theta should be equal to m plus half lambda. All right, let me explain why it's written that way. It's m plus half lambda, because when you give m the value 0, you're going to get 0 plus half, which is half lambda. But if you give m the value 1, then you get 1 plus half, which is 1.5 lambda. That's why the condition for darkness or destructive interference is d sine theta is equal to m plus half lambda. So here is a representation of the intensities on the screen. This is the central maximum. You see the intensity is maximum there. And then you have the first dark minima. And then you have the next maximum bright. Then again you have the next minimum and so on. So for this central maximum, m is equal to 0. For the next maximum, m is equal to 1. M is equal to 2, and for this m is equal to 1, negative 1, m is equal to negative 2. But when it comes to the dark one, the first one, m is equal to 1. So here there's a difference. So if I say, which is the value, what's the value of m for the third order maxima? You see, you got to go 0 is the central one. So if I'm calling it the third one, this is the first one, the second one, the third one. So for the third order maximum, m is equal to 3. Okay, so remember that when we do problems. And here I'm just giving an example. Consider that we have a certain slit width given, and just trying to show you how to use d sine theta is equal to m lambda. We can actually find the wavelength of light by using a setup like this, where let's say the distance between the slits is 0.01 millimeter. You see how small that is? The slits are really close. And we're measuring at an angle theta which is about 10.5 degrees. And lambda can be calculated using the formula d sine theta by m. Remember, this is in meter now. Now to change millimeter into meter, you'll have to divide by 1000. That's why it became 1 times 10 to the negative 5. And then you have sine 10.95 divided by m. And so the value of m depends on what order you see at that angle. So I'm assuming that you see the third order at that angle of 10.95 degrees. So when you do the calculations, you get the wavelength of light as 6.33 times 10 to the negative 7 meter, which is 633 nanometer. 1 nanometer is 10 to the negative 9 meter. So if you write this number, you can rewrite this as 633 times 10 to the negative 9, which makes it 633 nanometer. So here is problem number 2. Is this number 2? At what angle is the first order maximum for 460 nanometer wavelength blue light falling on double slits separated by 0.0500 millimeter? So we have to find the angle. It's the first order maximum, so we have the value of m. This is lambda, and you have the slit separation. So d sine theta is equal to m lambda is the formula. We're looking for theta. So when you make theta the subject, it becomes sine inverse of m lambda by d. M lambda by d. And you're like, oh, what is missing? Where is m? M is 1 because it says first order. So I did not put it there. Times lambda by d. And d is in millimeter, you got to change it into meters. And then you get 0.527 degrees. So it's that at that angle that you get the first order maximum from the center. So if the center is here, it's that tiny angle. Now, in all of these discussions that we had, we were talking about monochromatic light. That means light having a single wavelength. Okay, it was either blue or red or green or whatever. But what happens if you substitute monochromatic light with white light? Now, white light is a mixture of many wavelengths. So now the interference pattern is going to change. The central maximum is going to be white because all of the wavelengths will satisfy this condition d sine theta is equal to m lambda. Do you know why? Because for the central maximum m is 0. And so whatever is the value of lambda, 0 multiplied by anything is 0. And that when the right side becomes 0, you get the value of theta as 0 degrees. So for all wavelengths, the central maximum condition is satisfied, they all converge there, and you get white. But when you come to the other values, you see that because the lambda is going to be different, 1 times the lambda of blue will give you a certain wavelength, 1 times the lambda of red will give you another angle. So the angles are going to be different, therefore you see the colors on the screen not at the same point but at different points. Okay? And now you may be thinking, what's the use of studying all of this stuff? You know, it's really important because if you have a biopsy sample, by using optical imaging, in fact using interference, you can find out the wavelengths emitted by that sample. And that helps us determine the type of substances in the sample. So optical imaging of particular wavelengths in a biopsy sample is just one of the uses of interference. So here is the third question. What is the separation between two slits for which 620 nanometer orange light has its first maximum at an angle of 30 degrees? So this time it's the same exact question, but you're asked to find the little d, the separation between the slits. You're given the wavelength in nanometers, you're given the angle. So once again use d sine theta is equal to m lambda. You're looking for d, so make that the subject. M is the order and it says first maximum, so m is equal to 1. Wavelength is 620 nanometers, which is 620 times 10 to the negative 9 divided by sine 30, and when you do the calculations you get 1.24 times 10 to the negative 6 meters. Goes to show you how small the separation is between the two slits. We have question number 4. Calculate the wavelength of light that has its third minimum at an angle of 30 degrees when falling on double slits separated by 3 micrometer. So this problem has a difference. Number 1, it's talking about the minimum. So we'll have to use the condition for minimum. And then because it's minimum and it's telling us to find the third minimum, you see the difference. Again, on the left side is d sine theta plus, but on the right side, now we use the condition for destructive interference. So we're not using m lambda, we're using m plus half lambda. Why? Because it says minimum. You need to notice that. So we're asked to find the wavelength, so we'll make the wavelength the subject. But there's one more difference. When it talks about the third minimum, the value of m should actually be 2. Okay? And 2 plus half gives 2.5. Because it starts from 0, so 0, 1, 2, first, second, third. So that's why we use that. When we do the calculations, we get 600 nanometer. Remember, if it talks about minimum and it says the third minimum, use the value of m as 2. If it says the fourth minimum, use the value of m as 3. You got it. Okay? So that's the difference here. Which brings us to the next question here. It says, what is the highest order maximum for 420 nanometer light falling on double slits separated by 25 micrometer. So now we are asked to find the highest order maximum. We're looking for the maximum value of m. So lambda is given, the slit separation is given. Let's go into this formula again. It's talking about maximum, so we go back to d sine theta is equal to m lambda. Now, to get the value of m to be maximum, that means the right hand side should be maximum. You need the left hand side to be maximum. And that happens when sine theta takes its maximum value, which is 1. So in this problem, because we are looking for the maximum value, put sine theta is equal to 1 and calculate the value of m. So then sine theta is 1, then you have m is equal to d by lambda. D is, notice, is given in micrometers. Micro means 10 to the negative 6. So that's why it's 25.0 times 10 to the negative 6 divided by 420 nanometer. That's 10 to the negative 9. And you do the calculations, you get 59.5. But you see, m cannot take decimal values. It can only take integral values. So you round it up and say, hey, the highest order maximum that can be seen, actually it should be 59, because you only see 59 and a half. So the highest complete order that you see is what? 59. You only see half of the 60th. So technically the answer should be 59. Well, it'll be okay if you give 60, as long as you understand that m can only take integers, okay, integral values. That brings us to the next one again. That says calculate the distance between fringes. Now fringes means bands. Now what are we asked to calculate here? Calculate the distance between bands for 633 nanometer light falling on double slits separated by 0.0800 millimeters. So we have the wavelength, we have the slit separation, and then we have something else. What is that? Located 3 meters from a screen. So the idea is now we're talking about the screen, and the screen is 3 meters away from the slits. So these are the slits. You have the slits there. This is the screen, and there is 3 meter distance between them. And then what do we have to find? We have to find the distance between bands. So if you have on the screen, if you have the third maximum here, and then you have a minimum, and then you have the fourth maximum, right? So you're asked to find the distance between the third maximum and the fourth maximum. So that means you have to talk about m is equal to 3 and m is equal to 4, and then find the difference. Okay. So d sine theta is equal to m lambda, because again we're talking about maximum. And I set up this diagram here, which I will explain shortly. Okay, we'll come to that, but look at this. D sine theta plus delta theta, so is m plus 1 lambda. Let me explain that first. Okay, so for a certain angle, you get the third maximum on the screen, but for a slightly bigger angle, you get the fourth. You see, from the third to the fourth, the angle changes a little bit. So the value of m went up by 1 from wherever it was. Like if it was 3, it became 4. If it was 4, it became 5. That doesn't matter, because we're going to take the difference between the two equations. On the right side, on the right side, the difference is going to be lambda. Take a look, because this is m lambda. When you distribute this, it will be m lambda plus lambda. So m lambda plus lambda minus m lambda is going to give you lambda. So on the right side, the difference gives lambda. On the left side, we will neglect the sign, because when theta is small, sine theta is simply theta. So we need not look at the sign at all. That means on the left side, we're going to have d delta theta. d delta theta is equal to lambda. Rearrange that. You get delta theta is equal to lambda by d. And that's where, see, this is the distance of the screen. This is where the slits are. This is where the screen is. So delta x is the 3 meter given, and we just found the delta theta. And if you look at this, you know that delta y divided by delta x is delta theta. That's how you define angle. Yes, so delta y is delta theta times delta x. So from there, we are able to substitute for delta theta. See, we got delta theta as lambda by d, didn't we? So take that value, substitute here as lambda by d times delta x, and then we would be able to calculate delta y. So lambda is 633 nanometer, which is 633 times 10 to the negative 9. And then times delta x is 3 meter by d is 8 times 10 to the negative 5, because you have to change millimeters into meter. Yes, and then you get 0.024 meter. We have to talk about the diffraction grating. Or you're going to see this in the lab. A diffraction grating is a small piece of glass which has multiple slits on it. These slits are so close together that you would have like 5,000 slits in 1 centimeter. 5,000 slits in 1 centimeter. That means you make lines so close to each other. And what the diffraction grating does is, when white light passes through it, it breaks the white light into its colors. Because the wavelengths are different, the colors will come on the screen at different points. Now, the formula for the diffraction grating is exactly the same as that we've been using. So d sine theta is equal to m lambda for maximum. So that's what we will focus on. So in this question, a diffraction grating has 2000 lines per centimeter. At what angle will the first order maximum be for 510 nanometer wavelength green light? So the diffraction grating has 2000 lines per centimeter, so we need to find out the width of one line. How do you do that? In 1 centimeter, you have 2000. So what's the width of 1? 1 divided by 2000 centimeters. But we need it in meters. So we're going to do 0.01 divided by 2000, because 1 centimeter is 1/100th of a meter. I hope you're getting me. So first you have to find the width of one slit, which is 0.01 divided by 2000 in meters. Once you get that, which comes out to be 5 times 10 to the negative 6 meter, we use d sine theta is equal to m lambda. We're looking for theta, which is sine inverse lambda by d. Now m is 1, that's why I've not written it. And then you go, lambda is 510 times 10 to the negative, oh, that's a mistake. It's 510 times 10 to the negative 9. Okay, 510 times 10 to the negative 9 divided by 5 times 10 to the negative 6. Which is the little d, and then it becomes 5.85 degrees. That's how you work out a problem with a diffraction grating. Number 8, find the angle for the third order maximum for 580 nanometer wavelength yellow light falling on a diffraction grating having 1600 lines per centimeter. My goodness, isn't this the same question? Yeah, same type. So first you have to find the width of the slit, which in this case is 0.01 divided by 1600. Once you get that in meters, we can find sine theta using this formula. d sine theta is m lambda. Make theta the subject. Sine inverse 3 lambda by d. Why 3? Because it says find the angle for the third order maximum. third order maximum, so m is 3. And then carefully plug in the values of lambda. Lambda is 580 nanometer. I put it as 5.8 times 10 to the negative 7. I put 5.8, note that. And I calculate it to be 16.16 degrees. In number 9, calculate the wavelength of light. Now you have to calculate lambda. That has its second order maximum, m is equal to 2, at 45 degrees. Wow, now you're given the angle. When falling on a diffraction grating that has 5,000 lines per centimeter. First find d. What is d here? 0.01 divided by 5,000. Okay, once we get that little d, which is the width of one slit, we use d sine theta is equal to m lambda. M is equal to 2 because it says second order maximum. And then we figure out what lambda is using d sine theta by m. Okay? So that's d sine 45 because the angle is given as 45 degrees, which gives 7.07 times 10 to the negative 3 meter. That cannot be 707 nanometer. Well, I'll put that up as a correction on the screen. Look out for that. Next, we need to talk about resolution. I think everybody's heard about this word resolution. So if you on a whiteboard that's far away from you, if you put two dots really close to each other, really close, and you're seated on the last row, if the two dots are really close to each other, you wouldn't be able to tell if they are one dot or if they are two. So that's what you mean by resolution. The person seated on the front row may be able to make out that it's two different dots. But for the person who is behind, the two dots will appear to have merged into one. The reason is, for us to resolve, for the eye to resolve two dots as two, the angle that it makes at our eye should be at least 1/60th of a degree. 1/60th of a degree. So when we go further behind, the angle becomes smaller. When it becomes smaller than 1/60th of a degree, we see it as one dot. So that sets the limit for resolution of the eye. So here we got to talk about resolution of a telescope. You know, when you're looking at distant stars and you want to see if, you can separate them, if you can see them as resolved. So for that, we have a condition by a scientist called Rayleigh. It's called the Rayleigh criterion for resolution. Let me explain that. So here, it's actually diffraction that makes this problem, because light doesn't go just without spreading. Even if it's a laser beam, it's going to spread just a little bit. So if the spreading from two different points on the object overlaps, as shown here, see, like here, it's overlapping. It's the two different images of two different points on a star, so to say. If it overlaps, we will think that it's coming from the same point, while actually it's from two different points. So in order to say that these are two different points, the criterion is that the diffraction pattern of one, the first maximum of one, should at least fall on the first minimum of the other. Like the patterns shouldn't completely overlap. So if this is the first maximum of one, this is the first maximum of the other. It cannot be like this. It has to be in such a way that the first maximum of the second one coincides with the first minimum of the first one. So you remember the graph where the minimum comes here? So at least if they're that further apart, you can resolve them. So that's the criterion. Okay? So diffraction sets the limit of resolution. of any lens or any telescope or mirror, and then we'll have to look at this Rayleigh criterion and see how we can apply it. But here's the diagram, and so this is just the pattern of one of them. Here you have the pattern of both. You can see that the maximas are here of the first one. This is the maxima of the second one. But if you look carefully, you can see the minimum here of this one. So that becomes the minimum, and that minimum is right in line with the maximum of the other one. So if they are at least that much separated, you would see them as separate. That's the idea there. So now, since it's a circular aperture, we have to modify the formula. We can show that the angle should at least be 1.22 lambda by d. The 1.22 comes in because the shape has changed from a rectangular slit to a circular one. Because you know that cameras and telescopes, microscopes, the lens is in a circular aperture. So theta is 1.22 lambda by d. But a very important thing is that here theta is not in degrees, theta is in radians. Theta is in radians. Yes, you got to get that. So you got to set your calculator to radians. Be careful on that. And caps D is the diameter of the lens or the mirror or the aperture. Okay, so we'll be using that. But look at this. These are two different pictures taken by two telescopes. One is an Earth-based telescope. The other is the Hubble telescope, which is above the atmosphere of the Earth. And you can see that the resolution of the Hubble telescope is much better because there's no atmospheric disturbances for one reason, and it's a much better telescope, so its resolution is so good. It's actually the picture of the same thing taken by two different telescopes. It's a picture of the M82 galaxy. So you see what resolution can mean and can do. But here's a simple question. The headlights of a car, they are far apart. It's 1.3 meter apart. And then the question is, what is the maximum distance at which the eye can resolve these two headlights? Oh, so question is, how far away could you be to think that these two headlights were one? You know, if you keep going further and further behind from one particular distance, for sure the two headlights will appear to be one. So that's the distance we're looking for. Take the pupil diameter to be 0.40 centimeter. That's about your eye, okay? So here's how we do it. The formula, theta is 1.22 lambda by d. D is the diameter of the aperture. Lambda, here lambda, we're going to use the wavelength to which the eye is most sensitive. That's the bluish green color, and its wavelength is 555 nanometer, which is 5.55 times 10 to the negative 7 meter. It's good if you know it, but it will be given to you. And then 0.4 is in centimeters, so I changed it into meters. I hope that makes sense. So 1.22 times that by this gives you 1.69 times 10 to the negative 4 radians. So that's the angle. But we got to find the distance. So like before, from the angle, remember, from the angle, I gave you this relation, this 1.33. So that's one headlamp. That's the other one. The distance between them is 1.3 meter. And this is going to be theta multiplied by the radius. Okay, so theta, as long as theta is in radians, you can multiply. You can actually, if you divide these two, you get theta. That means theta times r gives you 1.3. Okay, let's see. Theta is 1.3 by r. So to find r, you rearrange, you get 1.3 by theta. We already have theta. Plug the value in. And keep it in radians. We need it in radians for this magic to work. Okay. You get 7,692 meters, which is 7.69 kilometers. Of course, you knew that you had to be very far away for you to see the two headlights is one. So that's how we do this problem. And now we come to the case of the thin soap bubble in sunlight appearing to be brilliantly colored. And remember what I told you about the oil slick, which also appears to be colored. Now what's common between the soap bubble and the oil slick? They are both thin films. For the soap bubble, inside it you have air, outside it you have air, and what separates them is a very thin soap film, of course. So here you have a film, a thin film. This could be oil on the surface of water. So you have three materials here. On the outside you have air, this is oil, and this is water. And so when light falls on this surface, light comes through air, falls on the oil surface, a part of the light is reflected and a part of it is refracted. That means it goes through. And the refracted part gets reflected from the surface of water and comes back up and then comes out into air. So when a person is watching this from here, the person gets two rays into ray 1 comes directly after reflection, so it travels a smaller path, while ray 2 goes from here. This is where they separated. Ray 2 goes all the way down, back up again and into the eye. So ray 2 travels a greater path, and the approximate path difference is twice the thickness of this oil film. Why approximately twice? Because it goes down, comes back up, and if this is t, then the path difference is 2 times t. So instead of saying d sine theta is equal to m lambda, you remember that d sine theta was the path difference. Here we're going to say 2t is equal to m lambda. But there is another problem. Whenever reflection happens, when reflection happens and an optically denser material, like when it tries to go from air into oil, because oil has a bigger density than air, there is an additional path jump of half the wavelength. Now don't worry too much about it, but when I write the conditions, I'm going to explain again. So basically I think you understood that the path difference is 2 times t. Okay, and here I've written it again. When light reflects from a medium having an index of refraction greater than that of the medium in which it is traveling, so like when it's going from air into oil, here there is a 180-degree phase change. So if a crest hits after reflection, it's going to come out as a trough, or there is lambda by 2 shift. So you'll see the conditions for maximum and minimum being reversed. That's what's going to happen. So the path difference is 2t, and instead of saying it's equal to m lambda, which is the condition for maximum, in this case the condition for maximum is going to be m plus half lambda. And if m takes the value 0, then you only have half the lambda. So that's why 2t is lambda by 2, because m is 0. So the conditions are reversed. This is the condition for maximum. 2t is lambda by 2. Now this is just an illustration of, if you take two slides and have a tiny drop of water between them, press them together, you are going to see colors on top of that. Or if you have the two slides kept like a wedge with an air film between them, and if this is illuminated with light from top, you're going to see colors. This is exactly because of what I explained before, because there's going to be a reflection from the top surface and the bottom surface, and when they reach the eye there is a path difference, so they could interfere constructively or destructively. Okay, so when we work out this problem, I think it should be easier to understand. So let's jump into it. A soap bubble is 100 nanometers thick. Goodness, that's really thin. It should have said 100 nanometers thin and illuminated by white light incident perpendicular to its surface. So the soap bubble is there, it's falling perpendicular to it. What wavelength and color of visible light is most constructively reflected? So we want to see, when you look at that soap bubble from a certain point, you want to see what color you're going to see, okay? For that, use the condition that I mentioned. 2t is m lambda, but m is what? M is 0. 2t is m plus half lambda. M is 0, so it's lambda by 2. But what lambda do we use? We have to use the wavelength in that material, okay? And the wavelength in that material is lambda by n. That's the first problem we did. So if the lambda in air is given, you have to first find the lambda in the soap film. How do you do that? Divide the wavelength by the refractive index. So that's why I've done that. And that means when you rearrange and make lambda the subject, you get 4nt. Okay? Why? Because look at that. Put this equal to this, and then you can see that the 2n goes here. So 2n times 2t is 4nt. N is that of water. That's 1.33. Soap mixed with water, right? So that's 1.33, and you have the thickness given as 100 nanometers, which is 1 times 10 to the negative 7, which is the same as 100 times 10 to the negative 9, same thing. And then when you do the calculation, you get 532 nanometer, which actually corresponds to the green color. So in this case, green would constructively interfere, and so that part of the film will appear to be green. Well, when you walk out in bright sunlight, you wear sunglasses. Now, if those sunglasses are just colored glasses, it's hurting your eye. But nowadays, all sunglasses, I should say, or most of them, are polarizing glasses. So now we're going to look at polarization of light. Why are sunglasses so cool? It's because in ordinary light, you have vibrations that are perpendicular and parallel. Let me show it this way, perpendicular and parallel. But what the sunglasses will do is it'll block out one of the vibrations, either the perpendicular one or the parallel one. Usually it blocks out the one that's parallel to the road, so it cuts out the glare. It doesn't block it out completely, otherwise we couldn't see anything. So that's what polarization means. Polarization means restricting the vibrations in light to one plane. Okay? That's what sunglasses do. So take a look at this picture. This is taken with a camera lens without the polarizing filter. So you can see the glare. But this one is taken with the polarizing filter in place. There is no glare and the picture is so clear. So this illustrates polarization. You know that if you have a slit in a cardboard and you hold a string and move it up and down, it'll pass through it because it's vibrating as the length of the slit is. But if you held it this way, if you try to make it vibrate this way, like along the x-axis, it will not go through because the slit is not wide enough, you see. So that kind of gives you an idea of polarization, restricting it. So this is ordinary unpolarized light, where there is all kinds of vibrations, and chiefly we're talking about the electric field, so that's why you have the E. But when you pass it through polarizing films, you see that the film just allows one vibration to go through. This is unpolarized. After it passes through the film, it's restricted to just one vibration. So that's what polarization is. And again, a couple of pictures to show you. This is really cool. If you see two Polaroid films And I'll show this to you in the lab, and it'll make more sense to you. You know, if you rotate one, you can see that it'll become completely dark. And then if you keep rotating, you can see through it. So both are polarized. And there are two laws that you need to know about polarized, and two formulas. One is the intensity of light that comes through is given by I is equal to I naught cosine square theta. Let me explain. I naught is the maximum intensity. So I naught is the intensity of this light, but after it passes through the polarizing filter, the intensity is I. And what does it depend on? It depends on the angle. So theta is the angle. We'll work out problems soon, but here is sunlight being reflected by something, maybe water. And you see that this is unpolarized light. Part of the light is reflected, part of the light is refracted or goes into the water. Both of these are partially polarized. That means it's not completely restricted to one plane, but most of the parallel vibrations, perpendicular vibrations given by the dots are here, and this one has most of the parallel vibrations. So that is partial polarization. All right, now, here's a definition coming up. If you change the angle of incidence, like if you bend it further and further, for one particular angle, you will get maximum polarization. Hear me out. For one particular angle, you get maximum polarization. That angle is called the polarizing angle. Write that down. Polarizing angle is the angle of incidence for which you get maximum polarization. Okay, and connected to that polarizing angle, there is a law called Brewster's law. According to Brewster's law, the tangent of the polarizing angle, your textbook calls it Brewster angle, so tan theta b. The tangent of the Brewster angle or the polarizing angle is N2 by N1. Real simple. What's N2, what's N1? You know, N1 is the refractive index of this material, and N2 is the refractive index of the material into which light is trying to enter. Okay? So we can work out problems now. The last three problems, I'm going to do them one by one. Number 12 says, what angle is needed between the direction of polarized light and the axis of a polarizing filter to cut its intensity in half? So that means I should be half of I naught. We're looking for the angle. Let's do this. We know the formula is I naught cosine square theta, and the problem says I must be half of I naught. And we're looking for theta. So cosine inverse I by I naught raised to half. Okay, now raised to half means you're taking the square root. Because you have cosine square theta there, you got to take the square root. That's what you mean by raising it to half. So what's I by I naught? I by I naught is going to be, come on, half. Because I is half of I naught. So when you do that, when you do the math, you're going to get 45 degrees. Number 13, I think I'd do it on the other side. 13, what is Brewster's angle for light traveling in water that's reflected from crown glass? Okay, crown glass is a type of glass. So the materials here are water and glass, right? So tan theta b is N2 by N1. N1 would be the refractive index of which one? What it's coming through. So that's water. N2 would be the refractive index of glass. And so theta b is tan inverse of N2 by N1. Both of these will be given. I've not printed it out, but it'll be given. N2 is given as 1.52 and water is of course 1.33. It's a good thing to know that. When you do that, you get 48.8 degrees. And am I glad that this is the last question we're coming to, number 14. At what angle is light inside crown glass completely polarized when reflected from water, as in a fish tank? Okay, so now once again you're finding the polarizing angle because it wants it to be completely polarized, so that's a polarizing angle. Tan inverse N2 by N1, tan inverse 1.333 by 1.52. Why the other way? Because now light is traveling from glass into water. Okay, from glass into water. So that's why first you have, and it's N2 by N1, correct? So that's why you have 1.33 by 1.52, the opposite of what we did before. And you get 41.2 degrees. This has been a great chapter. This is the last chapter in the semester. And I combined the lecture with the problems. That made the video longer, but I think it should make more sense when I try to combine them. I hope you look at these problems, make an effort to understand this, because this is so important for your exam number 3 and the final exam. Well, that's all. Signing off. We'll see you sometime in some other videos.